Compare a standard text file to a database. Stripping away their software icons reveals both dissolve into identical grids of binary. At the silicon level, these bits are stored on an SSD, sharing the exact same storage blocks and electrical reality. Both formats follow the same hardware path. They exist as bits on storage, move as pages into RAM, and are ultimately manipulated by CPU instructions operating on bytes in memory. In this macro view of a microchip, there is no database or text file logic etched into the silicon. The physical hardware provides storage and execution, but it offers no inherent intelligence regarding how data should be handled. Since the storage substance is the same, the question is not whether a database is physically different from a file, but what specific structures are being added on top of those stored bytes. To understand why a database behaves differently, we have to look past the storage medium and examine the machinery that manages the data. In a text file, data is stored as unformatted bytes on the disk. The OS sees a stream of bytes, forcing any search to proceed sequentially, line by line. The application code handles every detail, reading bytes, splitting lines, parsing fields, and determining columns. This flat file architecture leaves the data vulnerable. If the application crashes while writing a new line, there is no built-in mechanism to prevent the file from becoming partially written or corrupted. With a flat file, the intelligence required to search or protect the data lives entirely in the application, creating a significant management burden for the developer. A database changes this by introducing a dedicated architectural layer, the engine, which sits between the raw bytes and the application. This engine locks a schema grid over the data, defining its structure internally. The engine handles the schema, manages query processing, and search logic, removing these responsibilities from the application code. This split screen shows the difference in search cost. While the text file on the left requires a sequential scan of every line, the database on the right uses a specialized map to jump directly to the target row. The text file search is a brute force process. The CPU must read and parse every preceding character before it can find the specific record you requested. To avoid this, the database engine uses a B-tree index. This index is a separate structure built to optimize retrieval. It is an additional map of bytes that directs the CPU along a specific path to the data's physical location. By following these paths, the engine reduces the number of read operations, allowing for fast lookups even as the dataset grows. Databases further optimize performance by moving away from character-by-character processing at runtime. Instead of individual characters, the engine works with pages, fixed-size memory blocks moving between storage and RAM. Each page contains data, metadata, and pointers. The engine shuffles these pages between disk and a RAM cache to keep active data accessible. The engine's low-level task is to track which pages are current, which are modified in memory, and which must be written back to the physical drive. This page-level organization allows the system to manage massive amounts of data as modular chunks rather than one long, inefficient string of text. Protecting data integrity is critical during complex operations, like a balance transfer where you subtract from one account and add to another. If a crash interrupts a text file update, data is left corrupted. Databases solve this through atomicity. After a crash, the engine consults a transaction log to reverse incomplete work, ensuring a grouped change completes entirely or not at all. By following these recovery rules, the database ensures that the data remains consistent, even when the physical hardware fails during a write. This transaction logic provides a self-healing capability that guards against the state corruption common in simple file-based storage. Coordination becomes even more difficult when multiple users or processes attempt to read and write to the same data at the exact same time. In a flat file, overlapping concurrent writes can cause data fragmentation and a total collapse of the file structure. The database engine prevents this using concurrency control, applying locking and isolation rules to safely queue and process incoming requests sequentially. At this scale, the database acts as a traffic coordinator, enforcing strict rules over the bytes to maintain order amidst concurrent access. Industry-standard systems like SQLite, PostgreSQL, and Redis all rely on these same hardware primitives. Their differences are architectural, not physical. Each database makes different trade-offs regarding how they prioritize memory, enforce schemas, or model their storage. Every query follows a universal silicon-level flow. Data moves from storage into RAM, where the CPU executes the engine's instructions. The CPU parses the query, checks it against the schema rules, and follows the index paths that have been loaded into memory. It then reconstructs the requested data rows in RAM to return the final result to the application. Ultimately, the hardware remains a neutral executor. It simply carries out software instructions over structured data machinery. This comparison highlights the structural evolution from a simple file to a database system. A text file is a collection of raw stored bytes that places the burden of parsing and safety entirely on your program. In contrast, a database includes a powerful internalized engine that meticulously organizes, seamlessly updates, and flawlessly coordinates those raw bytes. A database is a software system that imposes organized meaning and operational rules on bytes. Its power comes from the rigorous intelligence built directly around the data.